Transformers Part 1, Theory, how do they work? First things first, let's talk about some different types of transformers and what's happening at a very high level inside the transformer. So a transformer is a device that transfers electrical energy from one circuit to another through induction. Usually the incoming voltage is the higher voltage and the outgoing voltage is the lower voltage, although that's not always the case. Sometimes that would be the case with a step down transformer. You may have a step up transformer that takes a lower voltage and then transforms it to a higher voltage. Or you might have something called an isolation transformer that just takes the incoming voltage and gives you the same outgoing voltage and just creates an isolation in the fact that there's no direct connection between the primary and secondary windings. The only coupling there is through the induction itself. So in the illustration we see here, we have two sets of wire or windings, and you can sort of see how that is describe how that makes sense to describe that as a winding, because it actually is a single wire that is winding around an iron core. So in this illustration, we see the top coil would be the primary coil. The bottom coil will be the secondary coil. And this is something you guys are all familiar with wiring primary and secondary sides of transformers, or most of you probably are. And so we have our incoming windings on the primary and outgoing windings on the secondary. And so that's the basic structure of a transformer. And the interesting thing about them is that with exception of a type that we'll go over in a minute, in most cases, the primary and secondary windings are essentially separate circuits. They don't physically touch. They're only coupled through induction, which we'll get more into detail about. So transformer types, what we see are single and three-phase transformers. In this illustration, these illustrations here, we see this one illustration that has a single a bucket. You might call that a bucket transformer. These are utility transformers. We don't touch these ever. But we see a single bucket. That single bucket is single phase. On the top right photo, though, we see three buckets on a pole. What that is three single phase buckets wired together to make three phase. And so if you look at this illustration in the bottom right, we can see that this is more of a typical configuration for commercial buildings. If we see a three-phase transformer, we're not really getting into this pole mounted stuff, but in a building, we'll see something like this bottom right illustration where you have an iron core that's separated into three sections. And then you have these primary and secondary windings. The primary windings in this illustration being on top, although this is not necessarily the exact construction of it, but as a pictorial representation, it gets the point across. We have a primary winding and a secondary winding, both wound around the iron core, one in each of three positions. So those are single and three phase. And so I have an illustration here that looks like something we're all used to seeing. There's a three-phase transformer. I don't know the size of this one. Maybe it's a 45 kVA. I don't know. But you can sort of see here in the picture where if you look past the wires, you can see these big blocks. And those are the windings. And what you can't see in the photo is that those are wound over the iron core. So if you just look at this photo here, and then look at this photo, you can see the relationship, like how this is sort of constructed. So this three-phase transformer is simply three single-phase transformers wired together. And so the way they're wired together are in two configurations. You have a delta-delta configuration and a delta-y configuration. Delta-delta would be where the three single-phase transformers are wired in a triangular fashion like this. So you have, we'll call this coil A, we'll call this coil B, and call this coil C. And we can see that C and A make a connection, A and B make a connection, and B and C make a connection in a triangular pattern. So you have one configuration where it's delta primary and delta secondary. Looks like I forgot to finish writing this slide. But delta is going to be used more like in industrial settings where you don't have a lot of need for a line to neutral load. You're going to, there is some benefit to delta systems to where if you lose B phase, for instance, because this is a closed loop, this is a triangular pattern, your system can still function, albeit at a lower capacity. Three-phase loads will still not function, but if you two-phase loads across A and C will continue to function, and to some degree from A to B loads or single-phase loads will continue to function, although not optimally. But there is some benefit to delta, and to where if you lose a leg, you don't lose everything. But they're not friendly to 120 volt loads. And so we won't see in commercial applications with a lot of 120 volt loads, we won't see a delta configuration. This is going to be more the industrial side of things, and also power distribution systems. Utility side distribution systems will use delta a lot because they don't need the neutral as frequently on those systems. Delta-wye, this is a configuration we will see very frequently, because what we're mostly doing are projects that have a good distribution of both three-phase loads as well as 120 volt line to neutral loads. So delta-wye is going to be the configuration. And so we can see the difference here between delta being wired in a triangular pattern. Y is wired in what you might call a star pattern, right? To where only one side of each winding is connected in the middle. And then in this next slide, I show where we would pull a neutral off of that middle point. So we're going to get more into the actual wiring of these transformers in one of the future classes. I don't want to spend a whole lot of time on wiring right now, but just wanted to point out that one of the key differences is if you did have a delta system and there was a neutral pulled off of that system, which in this illustration, you can see that the center tap of this coil is derived. That's called deriving a neutral, which just means grabbing the center of a coil. Is that you can get 120 volts, but you'll get what's called a wild leg or high leg, which by convention is typically going to be your neutral to B phase. By code, that's what we're looking for, although it could be any phase that is not the phase that you have derived your neutral from. So we can get into that in more detail and once we get into more wiring details. But in the Y configuration, you won't have that wild leg or high leg. It's going to be an equal split of voltage on your three-phase. And then there's another type of transformer that we would install occasionally called a buck boost transformer. And so the big difference between a buck boost transformer is if we go back and look at, I don't know if I had an illustration here, but if we could look at this illustration, we see there's no connection between the primary coil and the secondary coil. It's only connected through the inductive coupling there, right? There's no wire connection on in this one either. We can see primary coming in on one coil, secondary goes out on the other coil. There's no direct wiring connection between these. Whereas with a buck boost transformer, there is. And what this allows us to do is take an incoming voltage and either increase or decrease its voltage based on however we're wiring it. In a boost configuration, it looks like this, where line one or your high voltage circuit will come in and land on H4 and on between H1 and X4. And then one side of the secondary travels actually through the winding and also through the induction, increases the voltage on this other outer leg, which then gives you a 208 input and a 240 volt output. Whereas bucking that is the same exact transformer. It's just that we move where we terminate the X1 to a different location, and then it in turn bucks the voltage. Okay, that's as much time as I'm going to spend on wiring in this class. But some of these laws. So next thing we're going to talk about here is the theory, some of the core principles behind why transformers work, why that buck boost transformer would work, where we move by simply moving a wire, we are bucking the voltage instead of boosting the voltage. How come? Well, we have certain scientific laws, which I'm no scientist, so I'm going to explain this as best I can. But there are certain scientific laws that help to describe what's happening. So in this, we have Lenz's law here, which the scientific explanation, I'm just going to read it right off the page, is that Lenz's law states that the direction of the current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. It's a fundamental principle in electromagnetism and ensures the conversion of energy. So I think I've heard this too, where there's a principle of for every action, there's an equal and opposite reaction. So it's along those lines. So if you imagine that you're trying to push open a door, but there's someone on the other side of the door pushing back, that's basically what Lenz's law is. And then we also have Faraday's law, which is a bit of a longer explanation. Again, I'll just read it right off the page. The scientific explanation for Faraday's law is that Faraday's law of electromagnetic induction asserts that when a conductor is positioned in a magnetic field that is changing, that's an important part, a magnetic field that is changing, an electromotive force, EMF, is generated within that conductor. If the conductor forms a closed loop, and in this case, we would be talking about the secondary conductor. If the secondary conductor forms a closed loop, this induced EMF will create a current flow in it. The magnitude of this induced EMF in a coil is proportional to the rate at which the magnetic flux linked with the coil changes. The concept of flux linkage is crucial here. It is the product of the number of turns in the coil and the magnetic flux associated with it, represented as flux linkage, or number of turns times flux theta. Okay, that's a pretty fancy explanation. Let's go and let's read the simplified explanation to help us picture this a little better. So imagine, and you can actually do this. You could just get a simple magnet. I did this a couple of years ago where I took a magnet, I put it on the end of a drill, and then I took a coil of a coil of wire, placed it close enough proximity to that magnet, and just spun it. And I put a voltage tester on one end of the across the secondary coil to see if I induced any voltage, and I did. It was fractions of a volt, but I was able to produce some voltage. So if you imagine you're moving a wire back and forth near a magnet, so you can either move the wire or you can move the magnet. Imagine you're moving a wire back and forth near a magnet. As you do this, you create a sort of electric push inside the wire. If the wire is looped, this push can make electrical current flow. Well, when we say if this wire is looped, we mean if it's a closed circuit. Current can't flow in anything other than a closed circuit. So if you have a coil of wire inside of just one loop and you move the magnet, the push gets stronger or weaker based on how many loops you have and how fast you move the magnet. This relationship between the loops and the magnetic's influence is called flux linkage. Cool. So this will get more and more clear as we move through. So we've all played with magnets, as kids or maybe still as adults. But you notice there's an attraction, obviously. Opposites attract, right? Or if you try to face the same polarities together, they will push each other apart. That push and pull is caused by the invisible lines of force that are emanating from the magnet. So graphically, they're represented here, and the directions of the lines of force are directed here, or illustrated here. Right. So this is an illustration of a magnet and its lines of flux. In the lower illustration, we can see a magnet with lines of flux that have a wire wrapped around it. And the illustration is trying to represent to us that this will induce a voltage, but it won't induce a voltage if that magnetic line of flux or if the wire itself is static, if it's unchanging, if it doesn't move, it will not induce a voltage onto this other coil. The fact that it is moving is key. One circuit to another. The inducing implies there's not a direct connection, right? I suppose if you're like trying to influence somebody to do something, you're not controlling their hands directly, right? You kind of give somebody direction, you explain it to them in a certain way, and then there is some reaction that they will have, right? So in that way, like we could think of our relationships as a way of inducing somebody else to do something, or you might call that manipulation. um, so anyway, electromagnetic induction. So we're inducing voltages from primary to secondary circuits. And so what's happening in the transformer itself here in this illustration does a pretty good job of illustrating what we're discussing here. So we have a primary voltage coming in. The primary voltage magnetizes the iron core. So it's not, while there will be some sort of passive induction directly from the primary winding itself to the secondary winding, the magnitude of that is very low. And so we want to that induction, that force needs to be increased enough to have a meaningful change on the secondary conductor. And so this is where the iron core comes into play. And so you have your primary conductor coming in, wrapped around an iron core. It induces it magnetizes that iron core, right? We've done this before, probably in science class. Most of us have probably done this, where you take a wire and you wrap it around a piece of iron. When I was in school, it was a nail. Hook it up to a 9-volt battery, the nail becomes a magnet, right? And so this is what's happening here. We're wrapping a high voltage, let's say 480 volts, around an iron core, and we are creating a magnet. We're turning that iron core into a magnet. All right. And so that magnet now has its own electromagnetic field. So now we have two electromagnetic fields. We have the electromagnetic field created by the primary conductor. We have an electromagnetic field created by the iron core. Now, the iron core's electromagnetic field will induce a voltage into this secondary coil. And so if we watch this slide, primary is inducing into the iron core, creating a magnetic iron core. And now we can see that the secondary side now has voltage induced upon it. And if that secondary coil is a closed circuit, then electrons will flow in that circuit, which in turn creates its own counter EMF, which I don't think we've talked about counter EMF yet. So let me read the bit here about inductive reactance, just so we get that counter EMF principle in here. So inductive reactance is the relationship of inductive reactance. Okay, let me back up a little bit. So have any of you taken your voltage meter or continuity tester and put it across the transformer coil, primary or secondary? You go and you take a test. Oh, I want it before I turn on this transformer. I want to make sure I don't have any short circuits. Everything's all hooked up. You want to make sure you don't have any short circuits. You read from A to B, you ring out very low resistance or almost zero. B to C, same thing, no resistance. Oh, that's really head scratching. I don't feel really good about turning on this transformer. I got a short circuit. So you take everything apart, try to figure out where your short circuit is. You take all the wires off the transformer, you read it again, you still read a short circuit. Well, that's because you actually have a short circuit. And if this were just a resistive load, like a light bulb, then you turn it on, then yeah, you would have a short circuit. You would pull an immense amount of current. Circuit breaker would blow. So this doesn't happen in inductive loads, such as transformers and motors. These are called inductive loads. Resistance doesn't exist when it's at rest. Resistance exists when it is, in the case of motors, when there is movement, or in the case of a transformer, when there is a counter EMF produced by the magnetic core. So we have our primary coming in and inducing, and it has an EMF, and the lines of force are in a particular direction. So if we go back to this illustration, the lines of force induced, coming in on the primary are in one particular direction. The lines of force created in the iron core are in the opposite direction. And so what happens there is they cancel each other out. And that's called inductive reactance. And it's easy to remember that it's a reaction. It's reactance. It's reacting to something else happening. It's the same thing with when we talk about capacitors. You have capacitive reactance. It's the same thing. There's no resistance at rest. There's resistance when it becomes energized, when it moves. This is when resistance is introduced into the circuit or when it's reacting to something else. Okay. Okay, so that's pretty much inductive reactance. So the relationship of the primary EMF to the counter EMF, EMF is going to be short for electromotive force. Electromotive because electrons, motive because motion, right? So electromotive force, the relationship of primary electromotive force to the counter EMF inducing the iron core is called inductive reactance. And the relationship of the primary EMF to the iron core's counter EMF and the secondary currents, this isn't a real term, but I call it counter EMF, is how currents on the primary and secondary circuits remain proportional. As one increases, the other increases. As one decreases, the other decreases. Okay, so transformers use alternating current. This is important. Direct current transformers, not a thing. The reason being, and I don't have any graphic to represent this, but direct current, the voltage doesn't change, which means the electromagnetic fields induced by a direct current do not change. So if you had a way of moving the magnetic field created by a direct current, then you could actually say that direct current could produce alternating current, although it's probably very inefficient to do so. In most circumstances that we will see on this planet, alternating current is derived from a generator that is moved by means of steam, that steam being heated up by whatever fuel is being used to heat up water, produce steam, and turn a turbine, which in turn turns moves the stator, or moves the rotor inside of a stator in order to induce voltage. Okay, so alternating current. So how does that work? So AC voltage is being produced by a generator, right? Out at the power plant, a giant megawatt, giant generators producing all this power, right? So when the rotor inside of a generator, this is true of motors too, they're all constructed pretty much the same, is you have a stator. Stator is stationary, and that is going to be typically, but not always, I'm sure there's many constructions, but for the purpose of this explanation, the stator is going to be the outside radius of the motor. Inside that, you're going to have a rotor. Rotor spins. So stator, stationary, rotor, rotationary. So the rotor spins. Now the rotor, let's say, has permanent magnets. Okay. So we have permanent magnets attached to our rotor. Our rotor is going to spin. So since we're actually physically moving those magnets in a circular pattern, the stator has coils built into it. The stator has windings, just like the transformer does. So let me see if I can go back a little bit and show this illustration. So motors are basically transformers that spin. They work on the same exact principles, except one sits still and the other can spin, by the way it's constructed. So you have a primary winding. You have a winding here that's wound around the stator, right? And then this is actually what will end up having electrons flow on it and eventually make it to our homes and businesses, right? And so if you can picture that you have a rotor spinning here, and having the electromagnetic fields move through these windings, then you can picture that we have movement of the electromagnetic field. An electromagnetic field on that rotor, those magnets, that's fixed. That's a fixed value on those magnets on that rotor, right? Those electromagnetic fields themselves are not increasing and decreasing in magnitude. So what then causes an increase and decrease in our voltage in our system? Well, what's happening is as that motor spins, that electromagnetic field becomes, it starts at the outside edge of that stator winding. As it moves through, and then when the stator and the rotor are in their center positions with each other, so the center of that rotor magnet and the center of that stator winding are at, let's just call it top dead center. are in relationship to each other, that's when you're going to be at your peak voltage. And then as the motor continues to move, that electromagnetic field is going to move outside of that stator winding, and your voltage is going to increase. So I don't know if the way I'm verbally expressing this is coming across through it's coming across. If not, we can spend some more time on it. Get with me. We can spend some more time into dialing that in. Right. So that movement, that rotation, and that magnet cutting through the stator winding creates a rise and fall of voltage. And then that rise and fall will be in opposite directions, which is illustrated a little bit better in one of the further slides. Okay, so that brings us to sine waves. What is a sine wave? A sine wave is simply a measurement of voltage, magnitude, or amplitude over time. Okay, so a sine wave, basically, if you look at this, it's a sine wave. Sine wave is a circle cut in half and hinged, right? Like if you cut that circle in half and then you plotted it linearly, then it becomes this sine wave, this up and down form. And all this really is a measurement of voltage magnitude over time. Okay, so sine, if we remember from algebra, we learned about sines, cosines, tangents, right? And so the sine indicates the vertical distance from the x-axis, which is often represents time. So the x-axis on this chart is this horizontal line. That's your x-axis, right, which represents time, to its corresponding value on the y-axis, which represents amplitude. So this vertical line is your y-axis. It represents amplitude, or how much voltage we are producing here. And then we can see how your sine algebraically is this. If you see where it says 30 degrees, there's this vertical measurement here between the x and y axis. So that's basically what that is. That is your sine wave, right? So algebraically, this ratio of this line to your hypotenuse, I'm going to stop there. But all that is algebraically, this is called your sine. And so that's why we call it a sine wave. So a sine wave is nothing more than a measurement of the changing voltage over time. Okay, I just go into this a little bit because you hear people in the field talk about sine waves. But sine waves or sinusoidal motion, all that, this is not specific to our industry. You can measure, there are many things that you can measure via a sinusoidal representation such as this. But basically with it, what we can see happening here is if we have a motor at rest at 0 here, right? So if this intersection of x and y is 0, as the motor starts to move, you can see that voltage is going to increase to peak, then it's going to fall back down to 0 as the motor continues to rotate, and then it's going to go back to peak in the opposite direction. So we might call this negative. We might call this other amplitude positive, and then that cycle will continue to happen. Okay, so that's sine waves and how it relates to alternating current. And I just sort of like this graphic because it ties together what's happening in the motor versus what's happening in our sinusoidal measurements. On the left, we see a motor which actually uses a DC armature to induce magnetism onto the rotor and in turn induce voltage onto your stator, which is a little bit different than the explanation I had a little bit earlier. But yeah, so this illustration is pretty good for showing how the motion in the motor translates to a rise and fall in voltage. Okay, transformer ratios and ratings. Turns ratio. This is somewhat useful for us. All that theory is kind of neat. I'm probably going to forget this a week from now, just like anybody else here. But the turns ratio, this is kind of an interesting thing for us to remember, because if you want to try to figure out what your primary current is supposed to be, or you want to understand how we come up with how sizing of our overcurrent protection comes into play, understanding your turns ratio becomes relevant. And so the turns ratio is the number of turns on the primary winding divided by the number of turns on the secondary winding. So for most transformers that we see out there that have a 480 volt primary, in fact, all of them that are going to be 480 volt to 280 volt secondaries are going to have a turns ratio of 2.3 to 1, which means that for on your 480 volt side, so I'll go back to this illustration. So on your 480 volt side, this primary coil will have 2.3 turns for every 1 turn on the secondary winding. And this is interesting, right? So that how if we think about the which one was it, Faraday's law or Lenz's law? How I think it was Faraday's law. Where we talk, we have the magnitude of that induced electromagnetic force, or excuse me, electromotive force. Electromotive force being induced on the primary. If we wanted an equal voltage on the secondary, then it would be a 1-to-1 ratio, right? You'd have, for every 1 turning on the primary, you have 1 turn on the secondary. But since we are lowering our voltage, we want a lower number. We want less turns on the secondary than we have on the primary. Whereas if we were stepping up voltage, then we would need more turns on the secondary than we'd have on the primary. And so mathematically, if you have a 480 volt transformer, take 480 volt, divide that by 2.3, and you will have 208 volts. If we wanted 240 volts, it would be 2, right? 480 volt divided by 2, you'd have 240 volts on the secondary, which kind of makes me stop and pause and wonder, like, why don't we just create 240 volt secondaries? Probably where we're going to figure it out is because you wouldn't get 120 volts at your center tap, and then that would be a problem. So it's a trade-off. Okay, so voltage ratio. So the ratio of voltage on the primary to the voltage secondary is directly linked to turns ratio. We talked about that. With this information, what can we assume about the turns on the primary and secondary? We kind of went over this already. Okay, so the ratio of amperage on the primary to the amperage on the secondary, it's an inverse relationship to the primary, but that's sort of like, sure, cool. What we just need to know is that if the current flowing through the transformer is determined by the secondary load, right? The primary circuit, it's not what's producing the current. It's not the load. The transformer itself, well, arguably there are some losses in the transformer, so it is sort of a load, but only because of an efficiency loss. The secondary is what determines how much current is going to flow on the circuit, right? And so this is where we say current only flows in a closed loop. Remember, we talked about that with Faraday's law, where current only flows on a closed loop. So if you have 2 wires coming off your transformer and you connect a light bulb between them, that is closing the loop. We have connected a load across those windings on the secondary. That's closing the loop. Okay, so if our secondary amperage is 80 amps, we've closed that loop enough to where we are pulling 80 amps of current on the secondary, then we should have 33.7 amps on the primary. And that is simply by taking 80 amps from the secondary, dividing it by 2.3, and you'll have 33.7 amps. Now, of course, this is in a perfect scenario where there are no losses inside the transformer, which is not the case. So it won't be an exact 33.7, but you're going to be in that range of 33.7 measured on the primary. If you wanted to measure those losses, this is sort of an aside, but if you wanted to measure those losses, you would take a reading on the primary current, and then take a reading on the secondary current, and then try to figure out the difference of whatever is lost in the transformer. And then that can help you. And it probably is more sophisticated than that, but that's generally how you could figure out what your losses are inside of a transformer. Although we typically, as electricians in the field, aren't overly concerned with that. Kilovolt ampere ratings, KVA ratings. So KVA ratings, kilovolt amps, smaller transformers will be measured in VA. So K just means 1,000. So if we have a 45 kVA transformer, that means that transformer is capable of delivering 45,000 watts of power. A kVA rate is determine how many amps of current a transformer can handle at a given incoming line voltage. Interesting thing. I wasn't prepared to really talk about this, but it's sort of interesting to note that in a 3-phase load versus a single-phase load, you need to account for the phase angle, 120-degree phase angle. I'm not really prepared to talk about that. So I'll mention it, and I would say if you're interested in understanding how to calculate current flow on a on a three-phase system versus a single-phase system, reach out to me and we'll have some one-on-one time. We can dive into that. That's a bit mathematical heavy, and I don't think that's going to translate so well, and I'm not prepared to talk about it. But just know that there is a phase angle on three-phase systems that will produce a different voltage, or excuse me, a different current calculation than if you were only considering single phase. But the kVA ratings that we see on our transformers, that's the limiting factor on how much we can load that transformer up. And it's interesting that that relationship of your primary EMF versus the EMF produced in the core versus the counter EMF that's produced by the secondary is where, at least to a large degree, this limitation or this kVA rating comes into play. So if our secondary currents, as they increase, those secondary currents create a counter EMF in the iron core, right? So if we go back to maybe this photo, as the secondary currents increase, there's a counter EMF being produced. It's in opposite direction to the EMF being produced in the iron core in the first place. You have the primary trying to induce a certain magnitude of flux in that iron core. Then you have the secondary current doing the same thing, but in opposition to the primary. And then as that current increases in the secondary, it's going to cancel out. So that primary and secondary induced magnetism into the iron core are going to get closer and closer together until eventually they cancel each other out. And when they do, you've reached capacity. That transformer is no longer capable of producing any induction into that, any further induction into that secondary, because we've canceled out the electromagnetic field. And this is when the transformers are going to start to become damaged. It creates a lot of heat. Now we basically have a resistor. We are overloading our conductors and all of that. But this is where, and we'll get into this in one of the future classes, is how we size over current protection, how we size our primary and secondary conductors, why we have rules around all that. And it all plays into the theory of how they work. 741. Okay, but a little bit more time. Tying kVA ratings to inductive reactance EMF. I think this is what I just discussed. Sometimes I jump ahead. This is very math heavy, so we're not really going to get into this math too much. But yeah, the explanation of the primary to secondary to EMF to the EMF inducing the coil, that's what I kind of wanted to discuss with this. So we hit that already. Understanding secondary voltages. Okay, good. I wanted to have time to get to this slide. So something that's interesting that I see this on forums, for electricians forums, or individuals coming into the trade, or even people who have been in the trade for many, many years. If you get into like a home, like in our homes, we have single phase power. But if we open up our panel, we see we have A phase, we have B phase, at least we've identified it as an A and B phase, and we have a neutral. So the question that often comes up is, well, why don't we call this two phase? Well, this illustration here is really helpful for demystifying that. So the reason we call it single phase is if you look on the illustration here, our primary side, so this blue coil here, how many coils do we have? There's one coil here, right? We don't have two coils or three coils. There's one coil. So we have one coil coming in from our utility distribution system, right? Comes in, goes through their fuses here, primary input in their transformer, goes through their coil, and comes out on their neutral. I mean, it could come out on L2. It doesn't matter. What matters is that you have one path. There's one circuit. There is one coil. This is one phase, right? There is no other phase or phase angle or anything that is going to interact with this single coil wrapped around this iron core. Now, if we look at our secondary, that's pretty clear how this can be single phase when we look at the primary side. The confusion comes into play when we look at the secondary side. But the secondary side is also just one coil. Let's forget about the neutral for a second. We have one coil on our secondary side, which is has an inductive or flux linkage, right, with that primary side of one coil. So we have one coil here, and in order to get and then both sides of that we call L1 and L2. If we call them A phase and B phase, I suppose that's fine to call them that way, but it's not really an A phase and B phase. There's not two phases. We have two sides of one coil here. And the direction of current flow will change from one direction to another 60 times a second. But that's simply because this flux is being produced by a rotational, the cyclical movement of the generator, right? That's what's producing the oscillation, that change in direction of your electromagnetic field. But this is single phase. It's not two pole, not two phase or anything like that. And in order to get our neutral, all we're doing is we're just taking this secondary coil, which the longer distance of the secondary coil gives us 240 volts because there are more turns. The magnitude of electromotive force is larger across more turns. So we're just going to take from the center here, we're just going to grab that conductor in the middle, and then we're going to get 120 volts measured from either of the other legs. So that's single phase. The difference is still 240 volts, even when the phases are split by the neutral. So this sort of gets into the difference between single and three phase. It's interesting that this graphic is showing two different lines, but this is simply just where we're taking the measurement from. So this graphic could even be confusing to where I look at this, I'm like, oh no, I still have two legs. But all this is, when we're plotting this, is we're measuring this waveform relative to one leg or the other. So we could measure this one at a time, but what this is giving us is the measurement relative to which direction of current flow and when we are reading it. Three-phase transformers, three-phase connections have a phase angle of 120 degrees, whereas single phase doesn't. So that's another distinction between single and three phases. There's no phase angle here to measure against. So I think that's where I'm going to stop, because I really dove into studying the first third of this, and then the second third I think I need more time on. So I think we'll circle back to finishing this up next week when I can give you guys some better explanation of these things. I'll stop here. We have 13 minutes left. Who has anything to ask, anything to say, tell me what I said wrong, or some clarifications that anybody might have, or questions, whatever.
When in our applications will we use a buck boost transformer?
Oh, good call. So a common one that we might see is if we have a voltage drop issue. And so let's say that we have 240 volts at our point of service. So at our circuit breaker, we have 240 volts, but then we have a load of, we'll just call it, say 10 amps, and it's 300 feet away. Conductors are resistors, albeit they're really poor resistors. They're better conductors than they're resistors. That's why we call them conductors, but there is some resistance inherent in any conductor. And so the longer we go, the longer our circuits are, the more voltage that will be dropped across that load. That wire is in series with the load. And so if we studied series versus parallel circuits and how current relationships in a series circuit happen, we have a voltage drop across loads that are connected in series. So we may have, let's just say for the sake of the argument, that we have 10 volts have dropped across that resistor in series with the load. We're going to need to bring that back up. We're going to need to bring that value back up to what the load needs. If we have 240 volts and our load requires 240 volts to operate, or to operate optimally, then we would install a boost transformer in that circuit in order to get that voltage back up to an acceptable value. So voltage drop is a common-ish one. Sometimes I believe in recent history there was you'll get a piece of equipment that is rated for 240 volts, and type premises voltage is only 208 volts. Well, in that case, you would buck the voltage for a different reason, just to get it into within the specified range of that equipment. John, you had a question?
I was just going to touch on the last thing you said, that it wasn't, it was, yes, it occasionally is used for voltage drop, but the primary reason we use buck boosters is installing equipment rated for a different system at whatever we're installing the equipment at.
Yeah. So at the yeah. So either scenario, sort of. They're both sort of the same scenarios, right? Where we have to get the voltage within acceptable range of the equipment that it serves. Yep. Next week I'll try to get that 120 degrees. Explain the phase angle a little bit, and then we'll get into, I forget what it is exactly. Either next week is grounding and bonding of transformers, which also can help us understand, and grounding and bonding for services or separately derived systems of any type. I think that's going to be what's on the plan for next week. It'll still be on the topic of transformers, so 1 or 2 weeks on transformers. Yeah, and then if anybody has any suggestions for what to dive into next, maybe motors, how motors work. There's some relationships between how transformers work and motors work, so that might make sense to go into motors a little bit after we're done with transformers. All right, everybody. Thanks. Appreciate y'all.